In this video, let's finally talk about the PID controller. If you are ready, let's just dive into it. Previously, we have defined that the error is the difference between the target location and the current position. So in this example, the target location is 0 at the traffic light, and the car is about negative 100 meters away as the car is left to the target point. Then the error is 0 minus 100, so it will be positive 100, and that's our error at this moment. Then the car's acceleration will be the error times P gain. The P gain is the proportional gain and simply a constant that scales up or down to adjust the aggressiveness of the acceleration. Let's simulate this in our brain first. As the car approaches to the traffic light, the acceleration will lower down as the error decreases. However, the velocity has been increasing because the acceleration has never been negative. As the car is still on the left side of the traffic light, the error is always positive number. If it's like driving a car, you have been pressing the gas pedal less and less as you approach the traffic light. However, you have never stepped on the brake pedal. And obviously, this is problematic. Based on our definition of the error, there's no way we can slow down. If this is the case, the car will pass the traffic light with a high velocity. Then, the other side of the traffic light, the error will grow negatively. Then, the acceleration of the car will be negative and the car will finally start to slow down after passing the traffic light. Finally, when the car reaches to the traffic light again, the car will have a negative velocity, and now you know what's going to happen. The car will oscillate around the set point, which is the location of the traffic light. So we need to introduce a term like derivative of the error. By the definition of the derivative, it becomes negative as the error decreases. In other words, the derivative of the error becomes negative as the car approaches to the traffic light. Finally, we have the negative term. If this negative term is our brake pedal, how much aggressive you want to step on it is determined by the D gain, or derivative gain. By adjusting these two gains, finally, we can adjust how aggressive our autonomous car should be. Let's try this in the lab. To simulate with the exact same example as we have seen from the slides, let's try to use linear car lab. And then I'm going to connect it to the workspace. And then now let's create a new file, say my first PID.py. And obviously I'm going to copy the template and paste it here. Okay, to begin with, I'm going to delete this and I'm going to use timestamp and current position from the simulations message. So I'm going to turn on these two lines, and again I'm going to collect what's going on about the current position and timestamp. So I'm going to turn on these two to collect the data about the timestamp and position. Okay, actually let's collect the velocity too. And then after the simulation, I'm going to define the arrays of the state variables through time. And I'm going to plot the position and the velocity. So since we are giving 0 and there's not even a spring in this simulation, nothing's going to happen. So let's just say I'm going to give 1 meters per second square, just as an example to see what is going on here in this simulation. So make it 1, and then I'm going to type Control Enter to run the simulation. Then the car will just keep accelerating to the right side faster and faster, and then it will eventually go away because it's outside of the camera angle. And then as you can see, that's our position and then velocity. And velocity is kind of linearly increasing because our acceleration is 1. Okay, to return the car to our original position, just reset the simulation and that'll be it. Before we proceed, I noticed that during my video editing process, this part is omitted. So what I'm doing over here is that I'm making this timestamp array start from 0 by subtracting this all timestamp from the starting value of the timestamp. So by doing this, the timestamp will start from 0, and that's it. Now let's actually implement the proportional controller first. So to begin with, I'm going to define error. My error is target minus current position, which is pulse car. But I never defined the target previously, so I'm going to make it target is 0 because this traffic light's location is 0 and this starting position of this car is -7. So my error will be 0 minus -7, so it'll be 7. My error is 7. And then that will be proportionally related to my output. So my let's just say P out, which is proportional gain output or proportional control output. P out is error times a proportional gain. I'm going to call that proportional gain as KP. And my KP is 1 for no reason, just to start with. I just want to see what happens. And my P out is there. And since I'm making P out, I'm going to return it, and then I'm going to store this as my control output. I'm going to turn that on. So again, I have to turn that on too. So before I forget, let me make the title of the graph as well. That is position versus time. And then the second graph will be velocity versus time. The last one is the input or acceleration versus time, but I'm just going to go with input. So let's see what happens. It accelerated and then stopped at there, and there again it's kind of oscillating. And then the simulation stopped at a certain point, and then acceleration is 0, but the car had some velocity, so it just kept going to that side. So to make the car back to the original point again, just click the reset button. Anyway, so we have this oscillating graph, which is velocity here, and that's my position. Is this graph aligned with your understanding? Now let's see what happens if I make Kp to, I don't know, 0.02. Reset and run this again. I think this oscillation and the speed of car overall is getting lower, like it's moving slower. And then the graph is like this. And then what if the Kp is 10? Oh, by the way, currently it was like, it went up to 3, and previously when it was 1, the Kp was 1, it went up to 8. And then when Kp was 0.02, it was like, it was 6. And the velocity went up to 3. So I think, my point is that the amplitude is kind of lowering down, and then the period was extended. If we compare to this, we had this 1.5 period, if it's a sine or cosine graph. But now the period was extended here with the lower Kp. And now I want to see what happens if I increase the Kp to, say, 100. It's way faster, way faster. And then, whoa, what is this? This is exponential growth with oscillation. That's velocity, and then obviously the velocity was exponentially growing with oscillation. The position must be growing as well. And way faster, and then the period is shortened compared to the previous Kp. So this is about like how to adjust KP. If you increase the KP, the car will, where's my car? Car will respond more aggressively. If it is lower KP, the car will respond more in a milder sense. And in the next video, let's discuss the derivative term.